Good day, everyone. We are the Survey Design Group, and today we will be discussing the various concepts associated with survey as design. In order to understand the concept of survey design, we must first distinguish a survey from a census. To do so, we must first create a distinction between the concepts of population and sample. According to Graviter and Farzano, population is the entire set of individuals of interest to a researcher. Rubin and Babi define it as the theoretically specified aggregation of study elements, while Lake et al. Stated that, for epidemiological purposes, a population may be considered as groups of observation units, all with measurable or quantifiable characteristics. On the other hand, Leary defines a sample as a subset of a population, the group of participants who are selected to participate in a research study. O'Sullivan states that a sample is a subset of units selected from a larger set of the same units. The subset is used to infer something about the larger set, the population. Kerlinger and Lee define sampling as taking a portion of the population and considering it to be representative. This means that a sample is not necessarily guaranteed to be representative of the whole population. Rather, it depends on the researchers to define it as such. According to Rubin and Babi, a census is often similar to a survey, with the difference that the census collects data from all members of the population, and the survey is limited to a sample. Kerlinger and Lee state that random samples can often furnish the same information as a census, an enumeration and study of an entire population, at much less cost, with greater efficiency and sometimes greater accuracy. There are two overarching survey categories that are used for research: cross sectional and longitudinal. According to O'Sullivan, a cross sectional design collects data on all relevant variables at one time. Newman states that cross sectional research gathers data at one time point and creates a kind of snapshot of social life. Leary also reiterates that cross-sectional is a research design in which a group of respondents is studied once. On the other hand, Cohen et al. Report that longitudinal studies collect data from the same group at different points in time. Jackson states that, with a longitudinal design, the same participants are studied repeatedly over a period of time. However, this position is disputed by others, given that there are some studies classified under longitudinal design that are not required to use the exact same participants as before, such as the trend design, which we will discuss later. Jackson further states that, depending on the age range the researcher wants to study, a longitudinal design may span from a few years or months to decades. Longitudinal designs are also present in the field of medical and biological sciences. Lake et al. Established that longitudinal designs are conducted on test subjects or experimental animals through repeated monitoring over time. To further establish the meaning of cross sectional, let us examine a relatively recent example. In the month of July 2023, an Okta Research Group survey gathered responses from Filipinos regarding the question of whether the Philippines is going in the right direction or not. 72% of the respondents answered that the country is on the right path, while 11% disagreed and 16% were uncertain. This was a 13% decrease from the October 22 survey asking citizens the same question. This is illustrative of the term cross-sectional in that it provides data collected from a single group of respondents during a particular time period, specifically July 22 to 26 of this year. In this context, a survey, the research design focused on a single sample of 1,200 participants and examined what they thought during the time of data gathering. It is notable that the results differ via decrease in percentage of respondents answering that the country is going in the right direction, therefore exhibiting the quote unquote snapshot feature of cross sectional surveys. To illustrate, we can utilize a diagram. The square represents the population of adult Filipino citizens at the time of the survey, roughly around 68 million, and designated by the capital N. The sample is represented by the circle inside the population square. Within the circle, designated by the lowercase n, we can see that there are 1,200 respondents part of the sample. We can also see the specific year that the study was conducted, 2023. Going back to longitudinal design, we can examine the specific features that make a survey longitudinal. According to Leary, a longitudinal design is a study in which a single group of participants is studied over time. Distinguishing features that make a survey longitudinal include the focus on a single group of respondents, the fact that they are questioned more than once, and the possibility of studying changes in their behavior as they are observed over time. According to Rubin and Babi, longitudinal studies are those in which observations are made at many times. Such observations may be made of samples drawn from general populations or trend studies, samples drawn from more specific subpopulations, cohort studies, or the same sample of people each time, panel studies. We will now further examine the definitions of these three study types. According to Denzin, panel studies are characterized by the random selection of a group of persons who will be observed over a long period of time. Rubin and Babi noted that these studies examine the same set of people each time. A study of Lazarsfeld cited by Denzin gives us an example research problem. The impact of the mass media on voters' intentions from the beginning of the presidential campaign to the day of actual vote exhibits the features of a panel design. In order to make our illustration more relatable and easy to visualize, we can put the panel study and the following longitudinal types in the context of BA organizational communication students. Hypothetically, we can place the population number at around 200 students total. The representative sample called the panel is represented by the circle. We can see now that the panel has 30 members. Shown also are the years that the same individuals underwent study in intervals of 5 years: 2015, 2020, and 2025. For the next design, Rubin and Babi state that trend studies are those that study changes within some general population over time. Cohen et al. Note that trend studies focus on factors, for example, mathematics performance, rather than people, and these factors are studied over time. New samples, different people, are drawn at each stage of the data collection, but focus on the same factors, and if random samples are used, they can be representative of the wider population. Rubin and Babi give a specific research problem as an example: the identification of fluctuations over time in the number of social work students who specialize in various methods or fields of practice. Here we have the same example as before, utilizing BA Orcom students as our population. Using a sample of 30 participants, the trend design surveys for the first time in 2015, when the population of Orcom students is at around 200. The next stage of the survey takes place in 2020 to maintain the 5-year interval. In 2020, the population drops to around 180 as a result of factors like shifting and graduation. Therefore, a hypothetical shift in the sample size can occur, with respondents now at 20. Recall that these are not the same participants from the first stage, like in the panel design, designated by the distinctly separate squares. Finally, a third survey stage occurs in 2025. Our example illustrates that the population has again shifted, prompting a shift in the sample size as well. Note the overlap between the 2020 and 2015 circles. This means that a respondent from the earlier survey was randomly selected again as a member of the latest pool of participants, which is possible in trend design research. Lastly, we have the cohort study. According to Cohen et al., a cohort study focuses on a specific population in which all its members have the specific defining characteristic that is of interest to the researcher. Rubin and Babi note that cohort studies examine more specific subpopulations, cohorts, as they change over time. Furthermore, Rubin and Babi state that a cohort is typically an age group, such as the post World War II baby boom generation, but it can also be based on some other time grouping, such as people whose first episode of schizophrenia occurred during a particular time period after deinstitutionalization policies were implemented. For the research problem example, Rubin and Babi cite what happens to the incidence of substance abuse among young adults with schizophrenia as they age. In their example, a survey may take place in the year 2000 for persons with schizophrenia who are 20 to 25 years of age. In the following surveys, this same cohort will be reviewed, with such persons in the age range of 30 to 35 years being studied in 2010, those 40 to 45 years of age in 2020, and so on. Returning to our example of BE Orcom students, we will now narrow down the population to a specific cohort, BE Orcom students who are expected to graduate in 2025. The people in this subpopulation or cohort, designated by the lighter square inside the larger population, share the feature of being Orcom students. There is also a similar age range given that most of the people in the batch were born in the early 2000s. The subpopulation of the batch at the first survey period is around 55, shown above the sample circle. The number of respondents, 20, is once again denoted by the lowercase n, and the year of surveying, 2021, or batch 2025 students' first year, is indicated as well. In this hypothetical example, there are 3-year intervals for the stages of surveying. Therefore, the next stage of surveying takes place in 2024 or the student's third year. Here, we can see that the population shifts to around 50, which could be caused by students shifting courses or campuses. Finally, our third hypothetical stage of surveying takes place in 2027, when the batch members are fresh graduates of the university. The numbers of the subpopulation and the sample remain the same, given that the last stage of surveying was done during the student's third year when there is a very low chance of dropping out. Now that we have established some foundational concepts, let us discuss distinctions between units within target groups. According to Rubin and Babi, units of analysis are the people or things whose characteristics social researchers observe, describe, and explain. De Carlo describes it as the entity that a researcher wants to say something about at the end of their study, while Shepard defines it as what you would consider to be the main focus of your study. On the other hand, the Organization for Economic Cooperation and Development states that the data collection unit is the physical entity within the population about which information is collected, e.g., a person or a household. The synonymous term unit of observation is defined by De Carlo as the item or items that you observe, measure, or collect while trying to learn something about your unit of analysis. Shepard states that it might be the same as the unit of analysis, but that is not always the case. To illustrate, we can look at two different examples. According to Rubin and Babi, if you were to study the members of a street gang to learn about gang members, the individual, gang member, would be the unit of analysis. But if you studied all of the gangs in a city in order to learn the differences, say, between big and small gangs, between uptown and downtown gangs, and so forth, the unit of analysis would be the gang, a social group. In this case, the unit of analysis and the unit of observation are the same. However, there are cases when the two are different. For example, De Carlo states that if we were investigating gadget addiction in elementary school children, our unit of analysis, we might collect observations from teachers and parents, our units of observation, because younger children may not report their behavior accurately. De Carlo states that it is required for researchers to be clear about how they define their units of analysis and observation, both to themselves and to their audiences. De Carlo further states that your unit of analysis will be determined by your research question. Your unit of observation, on the other hand, is determined largely by the method of data collection that you use to answer that research question.
Let us now talk about correlation. According to Rubin and Bobby, being correlated means that changes in one variable are associated with changes in another variable. They also stated that correlation measures the strength of association with values that range from 0, which signifies no relationship whatsoever, to 1, which signifies a perfect relationship. In addition, Graviter and Forzano stated that it is a research strategy where two or more variables are measured to obtain a set of scores, usually two scores for each individual. Overall, they revealed that the purpose of a correlational study is to establish that a relationship exists between variables and to describe the nature of the relationship. So, what variables can be correlated? According to Graviter and Forzano, when a correlational study demonstrates a relationship between two variables, it allows researchers to use knowledge about one variable to help predict or explain the second variable. In this situation, the first variable is called the predictor variable, and the second variable being explained or predicted is called the criterion variable. An example from the authors is the relationship between graduate record exam scores and graduate school success. They explained that university admissions offices occasionally use the GRE scores to predict graduate school success. In this example, the scores are the predictor variable and graduate performance is the criterion variable. Leary stated that all analyses involve efforts to understand the nature of the relationship between two or more variables. He said that in most cases, these variables may either be discrete or continuous. He reported that a discrete variable is a variable that has a limited number of possible values. On the other hand, a continuous variable is one whose values fall on a continuum and can potentially have a large number of values. He stated that in general, all nominal variables are discrete, whereas variables that are measured on an interval or ratio scale can be regarded as continuous. Cohen et al. Reported that the number of illnesses a person has had and the number of meal times a person has each day are discrete variables, because in these examples, there are no fractions of a value. A person cannot have half an illness or half a mealtime. They either have the illness or not. They either have the mealtime or not. In contrast, he also explained that money in the bank, monthly earnings, numbers of students present in a class are examples of continuous variables because in these examples, there are equal intervals and for ratio data as zero. It is possible to have no money in the bank or to have no earnings or for a class of students to have none present that day. Next, we have categorical variable. Cohen et al. State that a categorical variable is a variable which has categories of values. They further provide one example. If we are looking at the types of food in school meals, we may want to have three categories: carbohydrates, proteins, and fats. Each of these is a category of the variable food. According to Reynard, categorical variables are discrete variables and as such are on the nominal level of measurement. Mertler reports that in many instances, nominal variables are typically expressed as dichotomies, either an artificial dichotomy, one to which participants are arbitrarily assigned, such as happy or sad, or a natural dichotomy, one that occurs naturally, such as left handed or right handed. We also have what we call participant and environment variables. According to Graviter and Wallnow, participant variables are characteristics such as age, gender, and intelligence that vary from one individual to another, while environment variables are characteristics of the environment, such as lighting, time of day, and weather conditions. So, what levels of measurement can be used for correlation? First, we have interval or ratio. According to Leary, for both interval and ratio scales, equal differences between the numbers assigned to participants' responses reflect equal differences between participants in the characteristic being measured. However, interval and ratio scales differ in that ratio scales have a true zero point, whereas interval scales do not. Graviter and Farzano also stated that ratio scales and interval scales produce numerical scores that are compatible with the full range of mathematical manipulation. A correlation that uses the interval ratio scale is the Pearson product moment correlation. Leary reported that the Pearson correlation is appropriate when both variables, x and y, are on an interval or ratio scale of measurement, as most variables studied by behavioral researchers are. Examples from Graviter and Farzano include measurements of height in inches, weight in pounds, the number of errors on a task, and IQ scores. Second is the ordinal scale. According to Leary, an ordinal scale is a measure in which the numbers assigned to participants' responses reflect the rank order of participants from highest to lowest. He also stated that when one or both variables are measured on an ordinal scale, in which the numbers reflect the rank ordering of participants on some attribute, the Spearman rank order correlation coefficient is used. Meanwhile, Graviter and Farzano reported that it consists of ranks or ordered categories. Their examples include classifying cups of coffee as small, medium, and large, or ranking job applicants as first, second, and third. Third is the nominal scale. According to Leary, a dichotomous variable is measured on a nominal scale but has only two levels. When correlations are calculated on dichotomous variables, the variables are assigned arbitrary numbers, such as male equals 1 and female equals 2. When both variables being correlated are dichotomous, a phi coefficient correlation is used. If only one variable is dichotomous and the other is on an interval or ratio scale, a point biserial correlation is used. Leary also reported that if we were looking at the relationship between gender and virginity, the former is appropriate because both variables are dichotomous. However, if we were correlating gender, a dichotomous variable with height, which is measured on a ratio scale, the latter would be calculated. Graviter and Forzano state that nominal scales consist of named categories. Their examples include eye color, academic major, or occupation. Leary reported that the relationship between any two variables can be portrayed graphically on x and y axes for each participant, we can plot a point that represents his or her combination of scores on the two variables, which we can designate as x and y. When scores for an entire sample are plotted, the resulting graphical representation of the data is called a scatter plot. According to Graviter and Forzano, to show the amount of consistency between two different measurements, the two scores obtained for each person can be presented in a graph called a scatter plot. They explain that in a scatter plot, the two scores for each person are represented as a single point, with the horizontal position of the point determined by one score and the vertical position determined by the second score. In addition, Argyros mentioned that in order to take account of the greater range of values that interval or ratio scales usually have, a scatter plot is the best way to organize such data to get an initial impression as to whether any correlation exists. An example of a scatter plot of the relationship between depression and anxiety was presented by Leary in his textbook. He explained that this graph shows subjects' scores on two measures, depression and anxiety, plotted on an axis, where each dot represents a single subject's score. For example, the circled subject scored 25 on depression and 70 on anxiety. As you can see from this scatter plot, depression and anxiety are linearly related. That is, the pattern of the data tends to follow a straight line. Let us now discuss about positive, negative, and zero correlation. According to Leary, a positive correlation is a direct relationship between two variables such that participants with high scores on one variable tend to also have high scores on the other variable, whereas low scorers on one variable tend to also score low on the other. He explained that the correlation between SAT scores and college grades is a positive one because people with higher SAT scores tend to have higher grades, whereas people with lower SAT scores tend to have lower grades. Here we have an example of a scatter plot showing a positive correlation by Graviter and Ferzano. They reported that this graph shows an example of a consistent positive relationship between two measurements. The relationship is described as positive because the two measurements change together in the same direction. Therefore, people who score high on the first measurement toward the right of the graph also tend to score high on the second measurement toward the top of the graph. Similarly, people scoring low on one measurement also score low on the other. On the other hand, Leary stated that a negative correlation is an inverse relationship between two variables such that participants with high scores on one variable tend to have low scores on the other variable, and vice versa. He explained that the correlation between self esteem and shyness is negative because people with higher self esteem tend to be less shy, whereas people with lower self esteem tend to be more shy. Here we have an example of a scatter plot showing a negative correlation by Graviter and Forzano. They reported that this graph shows an example of consistent negative relationship. This time, the two measurements change in opposite directions so that people who score high on one measurement tend to score low on the other. Lastly, according to Leary, a correlation of zero indicates that the variables are not related. Graviter and Forzano stated that if you measured shoe size and IQ for each individual in a group of third grade students, then you should find no relationship between the two variables. Here we have an example of a scatter plot showing a zero correlation by the two authors. They reported that this graph shows two measurements that are not consistently related. In this graph, some people who score high on one measurement also score high on the second, but others who score high on the first measurement now score low on the second. In this case, there is no consistent, predictable relationship between the two measurements. This figure by Leary shows several scatter plots of relationships between two variables. Positive correlations can be recognized by their upward slope to the right, which indicates that participants with high values on one variable also tend to have high values on the other variable, whereas low values on one variable are associated with low values on the other. Negative correlations slope downward to the right, indicating that participants who score high on one variable tend to score low on the other variable, and vice versa. Now, let us distinguish magnitude of correlation from correlation coefficient. But first, what is correlation coefficient? Leary stated that the correlation coefficient describes the strength and direction of the relationship between variables. According to him, when interpreting a correlation coefficient, a researcher considers two aspects of the coefficient: its sign and its magnitude. The sign of a correlation coefficient indicates the direction of the relationship between the two variables. Keep in mind that the sign of a correlation coefficient indicates only the direction of the relationship and tells us nothing about its strength. As for the magnitude of correlation, Leary defines it as the numerical value, ignoring the sign. It expresses the strength of the relationship between the variables. Ultimately, according to Hinkel, the correlation coefficient provides not only a measure of the relationship between variables but also an index of the proportion of individual differences in one variable that can be associated with the individual differences in another variable. The magnitude of the correlation, on the other hand, is only the numerical value and therefore a part of the whole correlation coefficient. Let us now compare and contrast the Pearson product moment, Spearman-Rowe, and point biserial correlations from each other. According to Graviter and Forzano, the Pearson correlation, usually identified by the letter R, is used to describe and measure linear relationships when both variables are numerical scores from interval or ratio scales. Leary stated that we can use the Pearson correlation if we want to study the relationship between test score and job performance. For example, he explained that if we are interested in whether scores on a particular test relate to job performance, we can obtain the employment test scores for 10 employees. Then 6 months later, we can ask these employees' supervisors to rate their employees' job performance on a scale of 1 to 10, where a rating of 1 represents extremely poor job performance and a rating of 10 represents superior performance. In the study Relationship of Work Engagements and Job Performance of University Teachers by Sitar, Pearson Product Moment was applied to examine the correlation between work engagements with job performance at university level. The researchers correlated the job performance and the dimensions of work engagement, vigor, dedication, and absorption among teachers of Central Punjab in Pakistan. The findings of the study indicated that there was a weak positive correlation between work engagements with job performance of university teachers. Graviter and Forzano stated that the Spearman correlation is used to measure and describe monotonic relationships when both variables are ranks from an ordinal score or have been transformed to ranks. According to the same authors, it is identified by RS and is simply the Pearson correlation applied to ordinal data. If the original scores are numerical values from an interval or ratio scale, it is possible to rank the scores and then compute a Spearman correlation. Leary reported that we can use the Spearman correlation if we want to study the relationship between teachers' judgment and their students' intelligence. For example, he explained that if we want to know how well teachers can judge the intelligence of their students, we can ask a teacher to rank the 30 students in the class from 1 to 30 in terms of their general intelligence. Then, we can obtain students' IQ scores on a standardized intelligence test. Because the teacher's judgments are on an ordinal scale of measurement, we calculate a Spearman rank order correlation coefficient to examine the correlation between the teacher's rankings and the student's real IQ scores. Dr. Okpala, through the study entitled The Measure of the Impact of Employee Motivation on Multicultural Team Performance using the Spearman Rank Correlation Coefficient, adopted the Spearman Rank Correlation Coefficient to measure a selection of 8 workplace indicators, namely gender, age, skills, cultural values, satisfaction level, teamwork relationship, level of motivation, and communication breakdown that address employees' motivation. A 5 point Likert scale was used to measure how these parameters influence team performance. Overall, this study shows a strong positive relationship between motivation and multicultural team performance. According to Allen, the point biserial correlation identified by RPBI is a measure to estimate the degree of relationship between a naturally dichotomous nominal variable and an interval or ratio variable. Leary mentioned that once calculated, the Spearman, phi, and point biserial coefficients are interpreted precisely like a Pearson coefficient. Allen also explained that, like the Pearson R, the point biserial correlation can measure two characteristics: direction and degree of relationship. The RPBI can range from -1 to +1, with 0 indicating no relationship, +1 indicating a perfect positive relationship, and -1 indicating a perfect negative relationship. The closer that number is to -1 or to +1, the stronger the correlation between the two variables. Brown reported that the point biserial correlation can be applied if a researcher might want to investigate the degree of relationship between gender, that is, being male or female, a naturally occurring dichotomous nominal scale, and achievement in English as a second language, as measured by scores on the end of the year departmental examination, an interval scale. A study entitled The Relationship Between Coping and Distress Among Faculty Members and Students During COVID-19 Pandemic Lockdown: The Moderating Effect of Gender by Darwish et al. Used the point biserial correlation to examine the relationship of gender, a natural dichotomous variable, with coping strategies and distress. The results of the study indicated significant relationships between gender, distress, and the three coping dimensions, namely task focused, emotion focused, and avoidance coping. It was also found that coping dimensions, as predictor variables, were significantly related to distress. Overall, this study revealed that gender moderates the relationship between emotion focused coping and distress.
Now we move on to another topic under survey as design: association. An association occurs if the change in the value of one variable causes a systematic change in another. For example, if the value of variable x increases and the matched values of variable y also increase, we can say that there is an association. To give a more concrete example, take body temperature and metabolism. As environmental temperature increases, the metabolism rate of animals who do not regulate their temperature also increases. This is an association, as the increase in variable x temperature causes a systematic increase in variable y metabolism rate. Association is essentially the statistical dependence between two given variables and points to a significant connection between these variables. Association can rise in the presence and absence of a causal relationship, as association does not necessarily imply causation, which will be discussed later on. It suggests only a hypothesis like a common cause, but does not offer full proof for causation. Association and correlation are sometimes used interchangeably in pieces of literature. They do, however, have their distinctions. According to Wolfer, an association simply points to a relationship between variables. To reiterate the points mentioned earlier, association points to two phenomena occurring together in a pattern or specific way. It is the co occurrence of specific events or factors in a way that when one thing happens, the other is most likely to be present. Take this scenario, for example. If the temperature is hot, people are more likely to buy sunscreens. Thus, there is an association between high temperature and demand for sunscreens, as when one variable, the hot weather, is present, the other variable, the need to buy sunscreens, occurs alongside it. Correlation, on the other hand, is a more specific statistical term and does not just refer to the existence of a relationship between variables. While association is the more general term and could refer to any linear or nonlinear relationship, correlation is more specific and measures a monotonic and often linear association between two numerical variables. Correlation is a statistical means of assessing an association. The strength of an association between two variables is quantified by the correlation coefficient R, which ranges from -1 to 1. Two variables are said to be correlated when they display an increasing or decreasing trend. Correlations help display the degree to which variables coincide with one another. Not all associations point to correlation. Figure 11.2c by Colasa et al. Shows an association between temperature and demand, such as high temperatures and demand for sunscreen, which is mentioned earlier as an example. This association, however, is not correlated since there is no linear relationship between the variables. Overall, an association is a more general term that refers to a connection or reoccurrence of two events. If one event happens or is present, the next event is likely to happen or be present as well. One variable provides information about another. Correlation, on the other hand, is a more specific statistical measure that examines an association between two variables and measures its strength through correlation coefficients. While linear and nonlinear correlations can be considered associations, not all associations, as mentioned earlier, are correlated. Though they do have their differences, correlation and association also have their similarities. Correlation and association both describe a relationship between two variables and do not always imply causation. While causal relationships can show high correlations, correlations do not show causation and are not identical to causation. The same thing goes for association. An example Altman and Krzyzewski give is the relationship between people who drink more than 4 cups of coffee and a decreased chance of acquiring skin cancer. This association does not mean that coffee causes cancer resistance. There may be a confounding variable, a variable affecting both observations, that could be the reason for the relationship. In this case, heavy coffee drinkers may have less sun exposure, which in turn could increase skin cancer resistance. So the cause may actually be the sun exposure instead of the coffee. Thus, association does not imply causation. It only provides a hypothesis, not solid proof. According to Healy, we can use a statistical association between variables as evidence for a causal relationship, but association by itself is not proof that a causal relationship exists. The variables that can be associated can be explained hand in hand with the levels of measurement used for association. To properly answer this question, we must have a quick review of variables and levels of measurement. The categories under the nominal level of measurement cannot be added, divided, or manipulated mathematically. Categorical variables, a type of variable under which nominal variables fall under, are variables that focus on distinct characteristics, attributes, or categories. The categorical variables used for the nominal level of measurement cannot be ranked. An example of this is the zip code, which cannot be ranked with respect to each other as they are arbitrary and cannot be manipulated mathematically. Variables under the ordinal level are called ordinal variables. Ordinal variables, which are also a type of categorical variables, are variables that can be ranked ordered, such as from high to low. Variables under this level of measurement can be classified as more or less than one another. An example of this is socioeconomic status, as middle class, for example, can be ranked higher than lower class and can be ranked lower than upper class. The interval ratio level of measurement makes use of continuous variables, which are variables that can be measured, quantified, or expressed numerically to show matters of degree. There are also often evenly spaced intervals between them. A characteristic of variables in the interval ratio level of measurement involve a true zero point. Ratio variables under this level of measurement have a fixed zero point, such as the number of siblings, since having zero siblings is possible. Interval variables can have no true zero point, with an example being temperature, as the value of 0 degrees Celsius or Fahrenheit does not mean that there is no temperature at all. Healy gives us a summary of the levels of measurement in Table 1.2. As mentioned earlier, this is Healy's table that gives us a summary of the levels of measurement and some examples. With this in mind, measures of association have been constructed for the following levels of measurement and their associated variables mentioned below. These tests give us information on the strength and direction of relationships, which in turn allow us to understand the importance or significance of relationships. The measures of association can help us trace causal relationships as well as document, measure, and analyze cause and effect relationships. Table 10.1 by Marquand Shapiro shows some examples of the levels of measurement and their corresponding measures of association. Reynard also shares a list of forms of association and correlation for corresponding levels of measurement and variables. Here are some examples from the list. Here are some examples of measures of association for nominal level variables, as well as nominal level interval ratio level variables. Then, here are some examples of measures of association for ordinal level variables, as well as ordinal level interval ratio level variables. Finally, here are examples of levels of measurement for interval ratio level variables to interval ratio level variables. The chi-square test for association measures associations between two categorical, particularly nominal variables. It is a common method for investigating a general association between two variables. For example, a chi-square test can be used to determine if there is a significant association between sex and U.S. political party. The various combinations would include male and female for sex and Democrat and Republican for the political party. Chi-square focuses on the difference of what is expected to occur and what is observed and primarily tests the null hypothesis, which is the hypothesis that states that there is no relationship between the two nominal variables. The difference between the observed and expected frequencies implies one of two things. It is either the difference is truly due to chance and there is no relationship between the two variables, or the values are so different that it cannot be said that the difference is due to chance, and so there is a relationship between the two variables, rejecting the null hypothesis in the process. It basically tells us the probability that a relationship between variables is the result of chance by establishing the significant existence of the relationship between the variables. With this in mind, the chi-square test has key differences with Pearson and other tests of correlation. One key difference is the level of measurement. The chi-square test primarily focuses on the nominal level of measurement. When at least one of the variables is at an ordinal or interval ratio level of measurement, the methods of correlation are used. The chi-square test also focuses on categorical, particularly nominal variables. While some tests of correlation, like the point biserial test, can make use of categorical variables, most tests use ordinal or categorical variables that can be rank ordered and continuous variables. Finally, the chi-square test cannot measure the strength of a relationship. It can only tell the significance of an association and that a significant association exists between two variables. The tests of correlation can test the strength and direction aside from the significance of the association. Here are summarized comparisons of chi-square and other tests of correlation. First, the chi-square and Pearson product moment. The chi-square test is non-parametric, meaning it does not make assumptions about the population the data was taken from. It focuses on the nominal level of measurement and categorical, specifically nominal variables, and measures the significance of the relationship. The Pearson product moment is a parametric test, meaning it makes assumptions about the data's populations and sampling. It focuses on interval ratio levels of measurement and continuous variables and measures the strength, significance, and direction of the relationship. Then, for the Spearman-Rowe test, one similarity is that they are both considered non-parametric. The Spearman-Rowe, however, focuses on ordinal level of measurement and ordinal variables or categorical variables that can be ranked. It also focuses on interval ratio level variables that are converted to ranked order, like the Pearson test that measures the strength, significance, and direction instead of just the significance of the relationship, as in the case of chi-square. Finally, for point biserial, their differences are that the point biserial test is a parametric test and measures the strength, significance, and direction of a relationship. Its similarity with chi-square, however, is that it does consider categorical variables. To be specific, it only considers dichotomous categorical variables wherein there are only two choices, such as yes or no.
So now let's go to the cross-tabulation table. The cross-tabulation table, also known as the cross-tab, two-way table, and contingency table, is a special type of table used to describe the relationship between two categorical variables. In other words, it is a numerical tabular presentation of data, usually in frequency or percentage form, in which variables are cross-partitioned. Now let's dive deeper into understanding the cross-tabulation table by discussing its parts. Here is an illustration of a 2 by 2 cross-tabulation table, or simply a cross-tabulation table of a bivariate analysis. The letters above, A, B, C, and D, represent the cell counts. A is the number of the observations corresponding to row 1 and column 1. B is the number of observations corresponding to row 1 and column 2. C is the number of observations corresponding to row 2 and column 1. And D is the number of observations corresponding to row 2 and column 2. Below these rows, we can see a total percent, and we may compute this by adding the rows 1 and 2, and according to the corresponding columns. Therefore, we must add A plus C and B plus D. Now, the furthest cell to the right shows the row totals, which indicate the sum of each row. Here we need to add A plus B, then C plus D, then add them all together like A plus B plus C plus D. By adding all of these, we can determine the total number of observations in each category and in the table overall. Now, to get a better grasp of the table, here is an example. In this example, we can see a cross-tabulation analysis, particularly showing the relationship between the two variables, with the row variable being the two genders, male and female, and the column variable labeled as alcohol, which shows if they drink or not. Now, the row sums and the column sums are sometimes referred to as marginal frequencies. Additionally, when you are describing the composition of your sample, it is often useful to refer to the proportion of the row or column that fell within a particular category. This can be achieved by computing the row percentages or column percentages. What we see right now are the formulas needed for computing row percentages. Now, notice that when computing row percentages, the denominators for cells A, B, C, D are determined by the row sums. Here, A plus B and C plus D. This implies that the percentages in the row totals column must equal to 100%. Now let's take a look at the column totals. If we look closely, we'd notice that when computing column percentages, just like computing for row percentages, the same denominators for cells A, B, C, and D are determined by the column sums. And again, this implies that the percentages in the column totals row must equal to 100%. And lastly, we have the total percentages. Notice that when total percentages are computed, the denominators for all the computations are equal to the total number of observations in the table, and this is A plus B plus C plus D. And then we have the box plot. Before we go to the illustration of the box plot, let us first understand the origins of the box plot. The origins of the box plot can be traced to the range bar chart. John W. Tukey's box plot became a popular representation and was introduced in 1977. The box plot, also known as the box and whisker plot, is a standard technique for presenting a summary of the distribution of a dataset. It is also one of the diverse family of statistical techniques called exploratory data analysis used to visually identify patterns. Overall, it is a simple yet powerful tool. And now we'll proceed to the parts of the box plot in order to visualize and better understand how the plot works. First, we have the extremes, the upper and lower extremes. The lines that are connected to the box itself are called the whiskers. Then we have the upper and lower hinges and the median that goes right in the middle of the box. We now know the essential parts that make up the box plot. Now let's proceed to the actual construction of the box plot. Flashed in front is a sample question and data collection. Now this may look quite intimidating to look at, but once this data is properly arranged, it will make the creation of the box plot much easier. So first, we must arrange these from least to greatest. After arranging the data, we must focus on finding the median, which could be found right at the middle part of the data. But if we are to compute for it, the formula for finding the median is n plus 1 divided by 2. If the rank is not a whole number, the average of the values immediately above and below this rank is taken as the median value. So, in this case, let's count the number of values in each dataset. We got 27 for the infants that died and 23 for the infants that survived. Then we should replace the n using these values, as n stands for the total number of values in a dataset. So let's use 27, add 1, we get 28, and divide the answer by 2, so we get 14. Therefore, we must count to 14, and we get 1.60 or 1.600. Now let's go to the next data set, which is 23 in total. So 23, we'll add 1, we get 24, divide the answer by 2, and we get 12. So again, let's just count to the 12th rank, and we get 2.20 or 2.200. So what this tells us is that the median for the infants that died is 1.60, and the median for the infants that survived is 2.20. Now that we got the median part down, let's calculate the lower and upper hinges of the box plot. Also note that there are other terms used for these parts. The lower hinge is Q1, also known as the 25th percentile. The median is Q2, and the upper hinge is Q3, or the 75th percentile. So now let's compute for the hinges. All we need to do is add 1 to the integer rank of the median. If the median is an odd number, then divide by 2. The integer rank of the median for the infants that died is 14, and it's an even number, so we can directly divide it by 2, and the answer is 7. Therefore, we must count to 7. And the answer for Q1 is 1.230. Count from below, and the answer for Q3 is 2.200. The same applies to the other dataset, which shows the infants that survived. The integer rank of the median for this dataset is 12, so we can directly divide it by 2, and the answer is 6. We then count to 6, and the answer for Q1 is 1.720. Again, count from below, and the answer for Q3 is 2.830. Now, how exactly do we find the extremes and the whiskers of the box plot? For these, we have to look at the lowest and highest point of our data points. Let's go back to our data sets. Right here, in the data set of the infants that died, we can see that the lowest value is 1.030 and the highest value is 2.730. Therefore, we must extend the whiskers to both of these ends, connecting them to the box. The same goes with the dataset of the infants that survived. The lowest is 1.130 and the highest is 3.640. Now, to visualize how these pieces of information look like, here's the representation of the box plots. Here are the upper and lower extremes, the medians, and the upper and lower hinges respectively. Now, if we look back at the data that we have computed for, these are visually accurate. Now that we know how to manually compute for each part that make up a box plot, how do we interpret the data? A box plot is meant to be used to interpret the data visually. We can interpret this by the comparison of location, dispersion, skewness, and outliers. The results in this case would show the mean birth weight of the infants who survived is considerably higher than the mean birth weight of the infants who died, and that the standard deviation of the birth weights of the infants who survived is also higher. Now let's compare them in terms of location. The figure shows that the median birth weight of infants who survived is greater than that of those who died. Comparison of dispersion. The interquartile ranges are reasonably similar as shown by the lengths of the boxes, though the overall range of the dataset is greater for the surviving infants. Comparison of skewness. Though both batches of data appear to be right skew, the batch for the infants who died is slightly more skewed than that of those who survived. The skewness is not particularly marked in either case. Comparison of outliers. Neither of these datasets shows any suspiciously far out values which might require a closer look. Overall, the two batches of data look as if they were generally distributed similarly, but with one batch located to the right of the other. You can see immediately that the median birth weight of infants who died is less than the lower quartile of the birth weights of infants who survived.